the integral over this region of the hole ends up being 0, I can equate the integrals of the boundaries. And since this is what I can do, I know that this line integral over that curve must be the same. So even though this is a rather troublesome conservative vector field, we got something out of it, a way to figure out the line integral over an arbitrary closed curve containing the origin.
Now what if you just had the inner circle and shifted it to the left to where it wouldn't contain the origin? Would it then work out?
Okay, so I shift it so it's no longer centered here, but it's still containing the origin?
No, so it no longer
No longer contains the origin. So in that case,
it would work out, right? It would
so because of this relationship, the integral would still be 0.
right.
Yeah. But then, if you shift this no longer contains the origin, then you open the door to curves like this that don't contain the origin either. So the picture becomes a little more murky in that case. All right, now, okay, I have 17 minutes. So now let's finally deal with polygons. Okay. Now, so in this case, we have a double integral that we want to evaluate that represents area, and we want to express it as a line integral to see if that could be evaluated more easily, and it turns out it can. Okay. So you have your polygon P that you want to compute the area of, and you want to express it as a line integral over the boundary of P with the correct orientation and all that, of an expression like this, P dx plus Q dy. Well, this has to be Qx minus Py. So we need to come up with a P and Q so that Qx minus Py happens to be equal to 1. Now, that's not hard to do. There's actually several choices you can make. So the choice we're going to make is this. We're going to let Q of xy be equal to x over 2, and P of xy be equal to minus y over 2. So then Qx is 1/2, Py is minus 1/2, so Qx minus Py turns out to be equal to 1. So now, we want to compute the integral over the boundary of P, so over all of the edges of a polygon of 1/2 x dy minus y dx. Okay. So if we can figure out how to compute this for each edge of a polygon and add all the edges together, then we got the area. So that's all it takes. And a line integral over a line segment won't be hard to do. So we're just going to pick one of the line segments, one of the edges, and work it out. And then we'll see how to write down a formula for the area of the entire polygon. Okay. So, so the edge we'll look at is from x1, y1 to x2, y2. And so we'll assume that everything has the proper orientation, that we've ordered the vertices in the correct way for that. So we need a parameterization for this. So parameterization we'll use is, now we'll assume, for convenience, that this is not vertical. So we at least have a slope to speak of. If it is vertical, that can be worked out separately. I ain't gonna do it. I did it in my head and was writing these notes, so my conscience is clean. Now, I could give that as a problem. Okay. So we'll let a parameter t go from x1 to x2. So then x will just be t, and y is going to be mt plus b. So this is a standard slope-intercept form of the equation of a line. So m is the slope, and b is going to be the y-intercept, so that's going to be y1 minus m x1. Okay. All right. So now what we can do is evaluate this line integral. So that's going to be 1/2 integral from x1 to x2. Now x is going to be t. dy, what is dy going to be? Good. So we need dy dt. Yes. Yeah. Okay. Minus y, which is mt plus b, dx, yeah, dx is just dt. Okay, well, we have t times m, we have m times t. Gone, gone. That worked out nicely. So now we have minus 1/2 integral from x1 to x2 of b dt, but that's just a constant, so it's going to be minus 1/2 b x2 minus x1. And now we'll fill in what b is. So we have minus 1/2 y1 minus m x1 x2 minus x1. Now, okay, so for the first part, we're going to have y1 x2 minus x1. And now, when we multiply the slope by x2 minus x1, x2 minus x1 is the denominator of the slope. So we get a cancellation here. So we're going to get minus y2 minus y1 times x1. So now this is what we have. And now we can simplify this. We have y1 x1 over here with a minus. We have y1 x1 over here with two minuses, which is a plus. So those are going to cancel out. So what we end up with, finally, is going to be 1/2 x1 y2 minus x2 y1. So that is a line integral over one edge of a polygon. So
Did you drop the 1/2 in your notes?
What?
Did you drop the 1/2 in your notes?
When I worked out the entire integral, so then you just have to put it back in.
Oh, okay. So
Yeah, so like, let's just take this, work it out, and then put it back.
okay.
Yeah. So now we can write down the formula for the area of a polygon by applying this same formula for all edges. So it's going to be 1/2. So we're going to have x1 y2 minus x2 y1 plus, and then we move to the next one, x2 y3 minus x3 y2, and so on, up to xn minus 1 yn minus xn yn minus 1. And don't forget to include the very last edge that goes from the last vertex to the first. So that's xn y1 minus x1 yn. There. So that is the formula for the area of any polygon with these vertices of x1, y1 up to xn, yn. And it took Green's theorem to come up with it.
Out of order. That means it's time to go.
Yes, it is time to go.
I have a question